Okay, I want to give you an overall perspective of what we are doing because you might think that we are coming back to our chapter 2, the random variables, and now there is a chapter that is somewhere in between, and now we are talking about some common probability distributions. So the chapter 2 gives you an overall description of what a random variable is, set the stage, and the probability density function or probability mass functions are arising from special situations. And in particular, the probability mass function that we talk about in discrete random variables come from some combinatoric problem, so which by itself has a certain structure. And the kind of probability mass that you find over there is somewhat more like a counting thing, which is combinatoric in nature. And then we come to the chapter 4 that give you a little bit more commonly occur random variables that people use, and people use to model it. And because they are so commonly used that it deserves, a study by itself. And then the chapter 3 is actually not only talking one variable at a time, but many variables that are jointly changing, which is, obviously the real situations, because we very seldom look at only one thing, but we look at multiple things, how do they interact together. All right? And now for the common probability distribution that we talk about, we are going to introduce the Bernoulli random variables. Next would be the binomial, and then geometric, and then the negative binomial. But these four distributions all belong to, you can think of it as the Bernoulli family, because the Bernoulli random variable is just you perform an experiment with only binary outcomes. Since it is binary, then we are taking it at either 0 or 1 for our coding. So binomial, you can think of fixing the number of trials that you are going to do. So for example, in multiple choice questions, n would be something like in our test is 15. And for each trial, you can think of it either success or failure. So the binomial is just many Bernoulli trials. All right, how many of them is prefixed. All right, so that is the most important distinction. The distinction between the binomial and the geometric that we are going to introduce, the geometric does not fix the number of trials, but I fix the very first success that I'm targeting. So I'm interested in counting how many trials in order to get the first success. All right. So in the binomial, I'm interested in counting how many successes in a fixed number of trials. Whereas in geometric, I'm interested in the trial, which is random, in order to get my first success. The negative binomial is I have a targeted, not just first success, my target is 4 successes, and so I wanted to keep trying Bernoulli trial until I accumulate up to and exactly equal to 4 successes, then I will stop. All right. So I go back to here. I think we have done this, but I wanted to say in words that it is easier to remember. The expectation of a Bernoulli random variable is just the probability of success. All right. And then the variance of a Bernoulli random variable is just the probability of success times the probability of failure. So 1 minus p is the probability of failure. So that would be quite easy to remember. All right. Now, so I will skip over this. And I think we talk about the roulette, and this is the American version. The American version, your probability of winning is a little bit less than the European roulette, all right? But anyway, it's still less than half. So on the average, how much you lose? If you pay $1, you will gain $1 with probability 18/38, but you will lose $1 with probability 20/38. So for each game that you play in a roulette, you will have -2/38. So it's about, say, -2/40, then it's about 5 cents, let's say, all right? 2/40, so it's 1/20. So it's about 5 cents per game. Now this margin is enough for the casino because they are not out to win everyone. They are out to win the collective gamblers. All right. So as some people might win, and some people, most of the people will lose. So collectively, they win. So they make money out of this with probability, not because for reputable casinos, right? For underground casinos, of course, they can do other things. They don't need to trick you. They can be very transparent, but because they basically use a law of probability to make the money out of you. So the best thing is, I think we probably won't have this, we don't talk about this. All right. So a box contains 4 blue and 6 reds. If a ball is drawn at random from the box, what is the probability that the blue ball is chosen? So this is, sort of an echo back to your chapter 2, which is combinatoric in nature. And I only draw one ball at a time. And my interest is on the color of the ball, which is blue. So I can think of it as success when I get a blue ball. If I have a red ball, I think of it as a failure. So here we have this. So this is very simple kind of combinatoric. Okay, so this is what we are up to now. So the binomial is Bernoulli trials. We are performing many. The emphasis should be independent Bernoulli trials. So each trials is independent of your past trials. All right. So roll a standard die 10 times. The rolling here, assume that you roll rigorously, so that suppose at the 5th roll, it would be independent of the first 4 rolls. So this is a basic assumption. And what is the number of times 6 turn up? So each roll, I think of a success when I get a 6. And when I get a 1 to 5, I think of it as a failure. So even though the die outcome is not binomial, but because of my interest is just focusing on 6, so I change the problem to a binary outcome, whether I get a 6 or not a 6. And then I do it 10 times. So n is fixed here. And what is really interested is not the individual 6, how the 6 appears. I don't care. What I really care is there are how many of them that turn out 6. So here a student randomly guesses at 5 multiple choice questions. What is the number of questions that the student guessed correctly? So it depends. So he has 5. And so he make independent Bernoulli trials for each of the multiple choice questions. So each question he has a success or failure, and then he do it 5 times. Now here we assume the multiple choice questions, the number of options here are fixed. either 4 for each question or 5 or whatever. So because we don't want the probability to change, all right? So meaning that if you use a die, then the other times you use another die which is loaded. So it's not the same thing that you are using. So you randomly pick a family with 4 kids. What is the number of girls among the kids? So you think of your things that you are choosing. First of all, the unit that you are choosing are family with 4 children. All right. So other family with either less than 4 children or more than 4 children will not be eligible in my bag. And so I'm going to pick one out of them. And so I'm interested in how many girls are there in this family. Now, okay, so we now consider a sequence of n Bernoullis, Bernoulli trials. Let xi denote the outcome of the ith trial. The result of the n trials then is a sequence of x1 up to xn. So the x tags exactly whether it's a success or failure at each of the trial. But this is not our interest. We are not interested in this vector of n binary entries, 0, 1. But I'm interested in summing up this vector, so which is x equal to this. Okay, and this will be the number of successes, number of ones in the sequence of n Bernoulli trials. Now, one of a very common mistake among students who learn this, they mistaken it like this. For example, if I'm just n equal to 10, so I have 10 independent Bernoulli trials. I specify the P. P is not, P is independent of the, P is the same throughout all the trials. A common mistake is I'm interested in the number of successes. So a common mistake would be X is a Bernoulli, and then you multiply by 10 because there are 10 trials. But this is wrong because what does this variable take? What are the possible values? It's either 10 or 0, right? There are only 2 choices because depending on whether x is 0 and then it's 10. So the one that we are actually interested should be this. Because each one is either 0 or 1 here, 0 or 1 here. And so this would be this. All right? So this is I mean, of course, if you are really pressed to about these questions, you probably won't make mistakes. I mean, students in the past. But sometimes students do slip into this when they are doing it very quickly, all right, because they simply multiply one of the outcome by 10. This is different from examining all the outcomes and then add them up. Okay, so first of all, we have a notation. Maybe we'll introduce a notation later. So this is the argument. Now suppose, okay, the argument here is trying to derive the probability of having x successes out of n Bernoulli trials. So one of the things first is I purposely put all the successes in the front. So in my first x trials, I get all successes, and then there's all the subsequent trials, n minus x of them, will be all failures. All right. So the probability for this particular outcome would be p to the power x, q to the power n minus x. Q is 1 minus p. All right. So because this is p, and this is p, and so because we assume the trials are independent, so the probability of getting a success in the first trial has nothing to do with the second trial and so on. So that justifies why we multiply the p and also the 1 minus p here. Okay, so we have this. But this is by no means the only one with X successes, because as long as you think of this as writing a word of n letters with which you only have X, out of which are S, and then n minus X are F. So this is just like forming how many words that you can form with n letters with only 2 choices of letter. You repeat the S X time, and you repeat the F n minus F time. And so the number of ways of doing it, if you still remember how we do the Mississippi things or Miss, is first of all, assume all the S are different and all the F are different. So you have altogether n different objects. So you have n factorial ways of arranging them. All right? But among those S, S1, S2, up to S small x, they are, if you erase the subscripts, the label, the S will not be distinguishable. Among them, there will be X factorial way of rearranging them. And because of this, you think of it as only one such case, rather than X factorial case. And this is the same as this. So I think the next slide is trying to do this, because this is actually equal to n factorial over X factorial times n minus X factorial. The bottom, the numerator, X factorial, is to discount the fact that all my successors are not distinguishable. And then n minus X factorial is to discount the fact that all the failures are not distinguishable, no matter what the positions are, relative to one another. So this is what we have the situations. So this is summarized in this. So a random variable X is defined to be binomial distribution. Now you have to specify this random variable with 2 numbers. We call it parameters. N is the number of trials, and P is the probability of individual trial success. All right, and this success is assumed to be constant throughout your n trials. Okay, and so this is the expressions here, and this only applies for x equal to 0 up to n, because you won't have negative successes, and you won't have n plus 1 or more successes. All right. Now it's a little bit of math here, but I don't think we want to emphasize this. So that's why the word here can be shown. All right. So the answer is, for the expected number of successes, on the average, it would be n times p. A better way to remember this is the number of trials times the probability of success. All right. So for each trial, you have a probability of success p, and the expected number would be the number of trials times the probability. And the variance is number of trials times the probability of success times the probability of failure. Okay. So it is quite easy to remember. And now when n equal to 1, it goes back to the Bernoulli trial, because I only tried once. And so you will see the formula will actually cover back the Bernoulli random variable when n equal to 1. Not only just the probability mass function, of course, then the expectation would be just p, and the variance will be p times 1 minus p. All right? So, so in a way, you can think of it as binomial. Bernoulli is just a special case of a binomial situations. The special case being that you only do it once. Okay. Now, I think it emphasized this point. Repeated means the p is the same here. All right. That is the emphasis. And then each of the trial is independent. So these are the 2 key points in the binomial. All right. And the fact that it is a Bernoulli trials, this sort of, so this is just expanding the explanation of Bernoulli, 2 possible outcomes. And so 2 possible outcomes, I will label it as either 0 or 1 in a binary fraction. And then what does the binomial do? the binomial counts the number of successes in n independent Bernoulli trials. All right? All right. Okay, guessing on the guessing on quiz. I think there might be some. Oh, okay. This guy failed to study for the next statistic quiz, and Pat's strategy is to rely on luck. The quiz consists of 10 multiple choice questions, and each has 5 possible options, only one of which is correct. And Pat plans to guess the answer to every question. What is the probability that Pat gets 2 answers correct, and then less than 5 correct, and fail the quiz? The part B is a dire reminder that the probability is very high. Okay, so if you are 100% not prepared, this is the reality. So at least you prepare a certain percentage. All right. So to get 2 right, purely by chance, by luck, you have 30% chance of getting 2 right, and then getting 4 or less, you have almost like 97% chance of failure. All right. So chance is not on your side. All right. Now maybe you can try this. Suppose you have 10 questions, and then this is point 2. Suppose you have 20 questions, and then it's still point 2. And now in our case, we want to have 10 in order to pass. So you want to calculate x is less than or equal to 9 for that particular 20 and point 2. What do you think? Will the probability go up or will the probability go down? Now this might be just too personal, but there are other kind of questions that are related to this. Suppose you are competing with someone stronger than you, you're underdog in a game. Now you can have a choice either out of 3 games, as long as any one of you have 2 wins, then you will win, or 3 out of 5. So now you are the underdog, but you have an option to choose since you are a weaker player. Would you choose 2 out of 3 or 3 out of 5? Or 4 out of 7, and so on and so forth? Okay, I'll let you think about it. All right? Okay. Now, how to calculate some of this probability? I will probably upload 2 files. I have to confess that I'm not really good in Excel. I'm really bad, actually, in Excel. I use R. You are okay. It's okay if you use a graphic calculator, whatever. But if you are just for passing this exam, it's your judgment whether you should invest in a graphic calculator. All right. But for the exam purpose, in the tutorial, we will not shy away from giving you some problem that you need either Excel or R. Another thing is that you can do is you can. This is just a little bit troublesome. You can have an online calculator. You just pick one that you are interested, and then that would be good. Because a few years ago when I taught a similar module, there are some favorite that I use, but I can't find them anymore. I mean, so it's being replaced. This is life, all right? Life is short here. Okay, so, I mean, but it doesn't mean that it's better. Actually, I'm not quite happy with some of the things that I've tried, the online calculator. What I'm going to upload 2 files is, one is on the Excel, some of the commands that you can use to calculate the certain distribution. If the file is not enough, watch YouTube, right? Okay. And also, but I will be uploading another file which is produced by Dr. Chu, David Chu. The Excel file is produced by Professor Chan, who is teaching the other sessions. And then the other PDF file I will upload is some of the R commands that you can use, all right? But you have to watch out in the PDF file, because when Dr. Chu was doing this, he has a way to link the examples to get the data from the slides. But after a while, we added in some other slides, so the slide number in the R code may not match. All right, so you should do it in itself. Now, let me explain a little bit here, since I'm a little bit more familiar with R. So there is a keyword here for the distribution, and you have to use binomial. All right, so this stands for the random variable you are looking at is binomial. D stands for density, and P is the cumulative probability. So maybe I'll just show you this. Okay, you can go to the help, and then there are menus, all right? So, for example, one of the menus is here. And so you can scroll to one of the chapter. The chapter is on distributions. So chapter 8. And then when you get to the distributions, I mean, it was a very steep learning curve for me, but I think you guys is in a better position than I was. But I have the advantage, I have a group of students behind me, all right? So now, these are the keywords for the distribution. Binomial, so these are the distribution, and this is how they recognize the command binomial, and then beta and chi-square and so on. And then now they have a word D for density, and then P for the CDF, the cumulative distribution function, and then Q is the quantile, meaning that if you specify the area is 50%, what is the number here? Now the P is you specify the number on the x-axis, and then you wanted to find out the area. So that is the percentile, the percentage. And then Q is the reverse. I specify the area and I wanted to find the number, okay? And R stands for simulations, for randomly choose things that have these distributions. And the things that you have to do is to specify the needed parameters. Now, if you remember the name, say beta or binomial, and you might have forgotten this, there is another way to seek for help. So, for example, you know this is a certain command, but you are not sure what are the arguments that you can put in. So, and then it will open up, some explanations. And the explanation is give you what are the options. Now, one of the drawbacks of R, as it is criticized, is that you have to know the menu. Just like you go to a restaurant, you have to know the menu. And then if you know the menu, then you know what to order, all right? The criticism against this is because R is actually working on a function. I mean, everything is a function. So having a function, you have to specify what are the arguments. But suppose you do not know there is such a function, then of course you can't use it. Just like you don't know this sandwich store actually give you nasi lemak, then you won't order nasi lemak, right? So that is the drawback. The best thing that people try to say is you have a waiter coming to ask you, prompt you what you might have options. So, but this is a drawback of R. But on the other hand, there are many fanatics in R that they write blogs, they do everything, and it's all for free. I think they really believe it should belong to the scientific community. Now, there is a software actually called S or S+, which is a commercial software. Some of the developers actually help develop S or S+, probably are not happy that they make a lot of money out of this. And so they wanted to make it free for the scientific community. And then people can actually write their own package, upload it, and then you also have the liberty to modify the source code. So you can actually tailor-make what other people have done in the package. And so you can create other things for your own purposes. So it is getting very powerful. So I think you should use it. All right? Now, so this is the command for this. So I guess it is very easy for you. Okay, so another one, 3 pointers. Ray Allen, I don't know who he is, probably is very famous. You see? No? He's probably not famous then. Hits 60% of the 3-point shots in catch and shoot situations. In a typical game, he takes 5 of such shots. Assuming each attempt is independent of the rest, and that he takes exactly 5 such shots, what are the probabilities that he will hit 4 of the 5 shots, and so on? Now let's try to do that. So 60%. So and we wanted to calculate 4, and that he's trying it 5 times, and that the probability of success is 0.6. So it's 25, 50, about 26%. Okay, and he hits at least 4 of the 5 shots. So that means hits 4 out of the 5. So that is bigger than or equal to 5, or it is because R only compute the probability or the cumulative probability from the left. So that would be 1 minus P binomial. You want it 4, so on that side would be 3 or less. All right, out of 5, and then 0.6. So I think this is it. This is about 34%. All right, so let's see whether, yeah, okay, so I get it. Now talking about this in here, there is, I don't know if you watch basketball, there is this thing called hot hand. I mean, someone who has been shooting very well. The whole idea of hot hands is to, will make the assumptions of independence not tenable, all right? Because the whole idea of hot hands is that he is, if he shoot a few times that he get it, then he will be more likely to get it again. So, okay, there are people who believe it, and there are people who actually analyze the sports data, and they sort of refute the hot hands theory. But anyway, here we assume independence, all right? It is known that screws produced by a certain company will be defective with a probability 0.01 independently of each other. Now this is, of course, one can argue whether it is independent, all right? Because if it's made by a machine, this is actually the assumption here is quite contrary to the production line. In fact, when people actually, when it's during the production line, people sample it. And then if there is a large number, by certain calculations, if there is a sizable number of defective, they actually stop the production line because the machines that is producing it is probably defective. Not just the screw, but the machine that produces it is defective. But here, for the sake of calculations, we assume whether the screws are defective. One good way to assume independence here is I assume these 10 screws are taken from different packages. So we assume that they are being produced in different batches. So there is a more reason for assuming independence, all right? And offers a money-back guarantee that at most one of the 10 screws is defective. At most one. It's a little bit strange, right? I mean, if I have 2 defective, that means I can't return it. Okay, anyway, this is English. It's nothing to do with probability, all right? So we'll look at the answer, and then we can understand what he's being asked, all right? So let X be the number of defective screws in a package. Then X is a binomial random variable, so this is okay. Now, one thing is, whenever you say something is binomial, you have to tell people what the N is and what the P is, all right? Hence, the probability that a package will have to be replaced is this, X bigger than or 2. So I guess, I don't know, I mean, I don't want to correct the English here. All right, so this is this. Okay, this is the guarantee. If you have at least 2 defective, I will replace the whole package, okay? So you can change the sentence in the questions. So this is this. Now, you can calculate this probability head-on. If you use your handheld calculator, what you can do is you have to calculate X equal to 2, X equal to 3, all the way X equal to 10. So you have altogether 9 numbers to compute. And for each one, you have to do the combinatorial button and then some power buttons here, right? So it's quite a number of buttons to press. It is easier to do the opposite of the problem. The opposite is either 0 or 1. So your calculation is reduced. But of course, if you are using a software, it doesn't really matter, all right? So it turns out to be 0.4% of the packages will have to be replaced, all right? So reasonably small amount. Okay. Okay. Now, a communication system consists of n components, each of which independently function with probability p. The total number will be able to operate effectively if at least 1/2 of its components function. All right. For what values of p is a 5-component system more likely to operate effectively than a 3-component? Okay, so now here we have to formulate the problem first. So n is known, n is either 5 or 3, but then the probability of functioning of a component is not known for p. So depending on what p is, you want to choose a 5-component system. Depending on what other p is, maybe 3-component is more reliable, all right? So this is how it's done. So the number of functioning components x is a binomial random variable with np. So for a 5-component system, that will be effective would be just 3 components, 4 components, and 5 components. Now, in fact, you can write it as 5 choose 5, p to the power 5, and 1 minus p to the power 0. But 1 minus p to the power 0 is 1. 5 choose 5 is also 1. So that is why it's just written as p to the power 5. So you have this. And then for two components in a three, at least two components in a three-component system functions will be given by this. So now the question is, what kind of P such that a 5-component is better? So in other words, you want these expressions to be bigger than or equal to this for a particular P. Now this is not a very easy thing to do if you do it by hand. Okay, so let's see how it goes. So for a 5-component system, more likely to operate, so I require this. And so you multiply it out, simplify it, and then factorize it. It is because P is always between 0 and 1, so this is non-zero, and in fact it is positive. So you can just delete out this and delete the 3. So as a result, P is bigger than half. So if your component is at least half reliable, the more components, the better. One of the reasons, maybe we will mention it at the very end, basically the law of large numbers say if you have many trials, the probability of success would be just the fraction of success. Now, suppose your component is 60%, so if you have a larger number of trials, then it would be closer to 0.6, the real value. And if it's closer to the real value and you are bigger than 60%, you are not an underdog. So as a result, it might be better to play more so that you will be more reliable. So back to the question that I asked, if you are a poorer player, say in table tennis, or whatever, then the other guy, the option to choose is to choose as few games as possible. 3 games, and then the best 2 out of 3, because chance might still be on your luck that you just happen to win 2 games out of the 3. But if you play, say, 300 games and you have to win 151, your weakness will be exposed by having played many games. So since you are a weaker player, the more games you play, on the average, your weakness will show up. But if you only play a small amount of games, chance will still be on your side that it hasn't shown your weakness yet. All right, so you have a better chance. Doesn't mean you will have a more than 50% chance to beat the other guy, but compared to many games and compare with a smaller number of games, you should choose a smaller number of games if you are the weaker player. If you are the stronger player, you play as many games as possible because in the end, your strength will show up. So in a small town, out of 12 accidents that occurred in 1986, 4 happened on Friday, the 13th. Is that a good reason for superstitious persons to argue that Friday the 13th is not auspicious? Okay, so we can calculate this. Suppose the probability that each accident occur on Friday is 1 out of 30. So we assume 30-day month, all right, just on any other day. Then on that particular 4 accidents on the Friday, so it would be 1 out of 30 to the power I, and then 29 over 30. 12 minus I, because you want it to be on that particular Friday. And then this is any other days except the Friday 13. And you have 12 accidents, and so you basically sum it up. So the probability of having 4 accidents is actually very small. All right? So since this probability is small, this is a good reason for a superstitious persons to argue that Friday the 13th is not auspicious. Well, more than not auspicious. It's dangerous, all right? So this is actually a reflection of many of our decisions or our thinking. If the probability is small, due to chance, then there might be some other explanations. So here the argument is that Friday 13 is nothing special or nothing bad as compared to the other 29 days. And so I do the calculations, and then I can't find that a good explanation due to chance. So this is really, really small. It couldn't have happened, but it did happen. So one of the scientific community argument is this is unlikely due to chance. If it's unlikely due to chance, I need a certain reason to explain it, all right? Okay, so this is it. So a man claims to have extrasensory perceptions. As a test, a fair coin is flipped 10 times, and the man is asked to predict the outcome in advance. So he predicts I have a head, tail. So meaning that actually for each guess, we can assess whether he get it correct or get it wrong. So basically, if he has extrasensory perceptions, in particular with the coin guessing, then he should have a higher chance of getting it right, all right? So what is the probability that he would have done at least this well if he had no extrasensory perception, ESP? So we try to do that, all right? Now, the assumption is that he had no ESP, meaning that he is simply guessing. And if he's simply guessing, he has a probability of 50% of guessing it right, all right? So we wanted to calculate a binomial of 10, and I have at least 7 correct answers. So this is actually what it is. So X is in 10 trials, a binomial, and it is because of the assumption of no ESP. That is why we can pin down the probability of right here, all right? So that is crucial. And then the probability of getting 7 or more out of 10 is actually not a small probability. It is about 17%. So if he purely guesses it, the probability is not small. So even though he does not have the ability to do so. All right? Some of you may not claim you have ESP, but some of you probably claim you can tell Pepsi Cola from Coca-Cola, right? I mean, or in a lot of blind taste tests, actually, I mean, it has a business implication quite some time ago. Pepsi Cola conducted a lot of blind tests. And then a lot of blind tests indicates that people actually prefer Pepsi Cola. They keep advertising it, okay? And then Coca-Cola is under pressure. Coca-Cola, on one hand, refute their study, all right? But at the same time, they know their study is probably has some ground. So they are out to do some, they are out to come up with a new Coke. So I think it was around 2000, Coca-Cola spent millions and millions of dollars, trying to find out the consumers, whether they prefer the new Coke versus the classical Coke. All right? So they do a lot of, they let them blind taste test and then ask them the questionnaire. And then it was a flaw in the questionnaire. They asked whether they prefer the new Coke. People say yes. But actually what Coca-Cola was thinking at that time was, if you prefer new Coke, I will only produce new Coke and I will stop the production of the classical Coke. All right? Now, but this is not what the consumer was responding. The consumer was responding that I also like new Coke. Now, so when Coca-Cola come up with the new Coke and then announce that they are stopping all the classic Coke, people uproar. They say the classical Coke belongs to USA. Now you are not producing it. Tell us the formula, right? Now, Coca-Cola sale actually plunge. And they also come up with other Coke, taste like medicine. Green, a little bit orange, pink in color. So, the business actually plunged a lot until they come up with heaven and earth. At least they stem the decline of the sale. Now, so a lot of these things is actually probably has nothing to do with this, but It has to do with even a questionnaire, the design is for a big company like Coca-Cola and spending maybe hundreds of millions of dollars in finding out the consumer preference. The question that they fail to ask one question, asking the consumer whether they want the new Coke to replace the new Coke, but they ask whether they like the new Coke over the old Coke. Then the wording is wrong, and so $100 of millions down the drain, all right, and their reputations. Okay, maybe we'll stop here. So let's come back at 11, and we'll try to finish some other discrete random variable.
For this question, why we cannot use 1/4 since there's like 4 Fridays in a month?
Oh, no, there is. There's one particular. Okay, this is it. So actually, even the guy who get it 70% of the time doesn't mean he is actually he has the ESP. Simply because the probability here is almost like 17%, which is not small. So, yeah, so he might be able to fool you. So for this kind of situations, 0.5 and then do it 10 times is not large enough, basically. If you want to tell apart whether he does not have ESP or not, then you might want to have 20 and then see whether you have, the guy will have something like 15 or 14 correct. Okay, 14, at least 14, that is still 70% correct. But now you let him have 20 trials or even more. The whole idea is that if his actual probability is 0.5, if you let him try more, it would show up. All right. If you do not let him try enough, then he might still have a good chance of getting more than half right. All right. So, of course, when I say good chance, doesn't mean it is 0.5 or above, but here it is not negligible. It's not a small probability here. All right. Okay. So I think basically the situation is more or less the same. So is the whole point of all this example is, the first thing is ask yourself, now because in this example we are in the binomial sections, of course you know it would be a binomial. So the real thing in real life is to decide whether a binomial is the right random variable to use. All right. Once you decide that it is random, binomial. So to have a binomial, basically the thinking is the thing that you are looking at consists of many, many steps. And so the number of steps will be the number of trials. And then each step would be either 0 or 1. So it's a binary outcome in each step. And the other thing that you have to watch out is whether each of the steps are independent of each other. Now, of course, this will require some kind of a judgment, whether the individual trials are independent of one another. Now, this is not so easy because it basically either you spell out your assumption or you really think so. Back to the basketball thing, I mean, like the free throw. If you believe in hot hands, then you basically don't want to believe in independence. All right. So it really, I mean, basically ask yourself whether it would be reasonable, at least your conscience, whether they are independent. Now, for academic exercises, there is no big consequence whether you decide independence or not independent. At most, you just fail that questions. But sometimes, for example, even for basketball game, I mean, at the very last few seconds, the coach call a time's up and then formulate a strategy. And the coach probably will say, pass the ball to this guy. He's hot now. So, I mean, that might determine the game, whether it is will lead to a final win or, a loss, all right? So it has consequences. The first probability, okay, so I'm not going through this. It all is in some kind of a modeling, all right? Okay. So here, this is the situations. When you plug in n equal to 1 back in the binomial formulas, then it reduces to these situations. Now, this is a shorthand notations of this because when x is either 0 or 1, it would be, if x is 0, basically this term will not appear because it will be 1. If x is equal to 1, this term will not appear because this is 1. So you will have your usual, if you wanted to write as a table, you have either 1 minus p, 0, and then 1 is p here. So it's the same, all right? Okay, geometric random variables. So this is another random variable that are related. The cousin of the Bernoulli family. All right. So a random variable x is defined to have a geometric distribution. So this is the mathematical formula. All right. So, but I think it would be better to explain this first. The random variable x counts the number of trials required until the first success is achieved. Now, in this notion, I also count the trial that has the success. So I'm including the trial that leading to the success. Now, if this is the first success, what does it mean? It means that anything before has to be failures altogether. All right. Now, this is by no means the only one, but let me not confuse you at this point. But let us try to derive this. Okay. So here it means this. Okay, so this is the first trial, and this is the x trial. And this is the x minus 1 trial. And now, according to the meaning here, this is a success. All right? And this is the first one. So if this is the first one, what does it mean? It means that all of them are failure. All right? And so this is 1 minus p. This is 1 minus p, this is 1 minus p, and then this is a p. So as a result, this is 1 minus p to the power x minus 1 p. Okay, so here the convention is I count this trial also. So this is the total number of trials in order to get the first success. And this probability is given by this. All right? Okay, so what is the expected value? Now, for the geometric, it means that on the average, how long you have to wait until you get the first success. So this is, the meaning is on average, how many trials do we need in order to get the first success? Okay, and this is 1 over p. All right, so this is the formula. It's just some math thing, all right, which I don't want to bother you. But the answer makes sense because it has to be inversely proportional to the probability of success. Now, whether it is 1 over p squared is another matter, but it has to be a decreasing function, right? Because when p is smaller, meaning that getting a success is very difficult. In other words, that means you have to wait longer in order to get the first success, right? Suppose you flip a coin, getting a head, you don't expect to wait very long. But if you consistently buy total, the 6-number thing, you know the probability of striking the first prize is really, really small. 1 out of almost like 14 million. So you won't expect, even if you keep buying it, you know you have to wait a long, long time, right? So this is saying this. If the probability of success is very small, you have to wait longer. If your probability of success is larger, you don't expect to wait very long. So this is it. Okay, now another thing is the variance is equal to 1 minus p over p squared. So in other words, the standard deviation is actually this. It is almost like 1 over p, but it is corrected by this. If p is very, very small, this is almost like 1. So basically, the standard deviations and the variance, the standard deviation and the mean is almost the same, all right? Now, if you have some idea, the standard deviation means the things you expect it to happen at 1 over p. Let's say p is 1 in 1,000. So you expect to wait 1,000 trials in order to get the first success. But there is a lot of variations here. The variation is 1 minus p over p squared. Let's forget about 1 minus 1 over 1,000. So this is almost like 1 because this is 0.999. So the standard deviation is also 1 in 1,000. Okay. So now what it means is you expect something that you have to wait for 1,000 trial, but the standard deviation is plus or minus. So it might happen very early with a very small probability, but it still happens. Or you might have to wait not just 1,000 trial, but you might have to wait much longer, almost like twice of it, say 2,000 trials. So it is because the standard deviations for p is small. The standard deviation is something like 1 over p2, which is comparable to this. All right. So okay. So we have this. There is, unfortunately, there are two versions of geometric distributions. So when people tell you about is the geometric distributions, either you have some telltale signs, which I will tell you, and then, or another thing is to check with the person whether the last trial, which leads to the success, will it be counted. All right. So here in the versions, we only count the number of failures until I get the success. So I'm not counting the last one, the one that I have a success, but I only count how many failures I have. So basically, this version and the previous version differ by 1. Okay? Is that all right? Okay. So the version here, y is equal to x minus 1. Now, the telltale sign is the following. The smallest value of y here starts with 0 because 0 is realizable. Because you might have 0 failure and then you have the first success. Since I do not count the trial that leads to the success, so I basically have, in other words, I have 0 failures. So I start with 0. But if you look back, I start with 1. That is the smallest possible number because you need to count the trials, including the one that leads to the success. So you have to start at 1. So either you look at the density definition, then you can tell whether it is this version counting the total number of trials, including the success, or you are counting the total number of failures. All right? Not counting the success. Okay, so the formula differs a little bit. Y is a little bit less than x, so as a result, the expectation of y is a little bit less than this. In fact, if you are willing to accept the results earlier, I can derive this without much pain. All right, so let me do so. So you remember this, expectation of x is equal to 1 over p. But now your y is equal to x minus 1. So you exclude the trials that has the success. So your expectation of y would be just expectation of x minus 1. So this is 1 minus p minus 1. So it is 1. So you have this. And then the variance of y is the variance of x minus 1. But you remember that this is just a constant. So translating things will not change the variance. All right. So so the slides in your lecture notes 611 can be derived from the previous slides. All right. Okay. So let us denote the number of semiconductor wafers that need to be analyzed in order to detect a large particle of contamination. Assume that the probability that a wafer contains a large particle is 0.01 and that the wafers are independent. Determine the distribution of x. Okay, so you keep on testing individual wafer until you find a wafer that has something like a size of 0.01. So this is it. All right? All right, so the P here, the success probability, it is actually a failure probability in some way because it is not good. It is the probability of defective here. So it is this. All right, okay. So maybe I should emphasize that in the Bernoulli thing, P always a thought of success, but the success is in quotation mark, all right, depending on what you're looking at. It might be a failure, but you are interested in the failure, then you call it as success, all right, in that sense. Okay, a drunkard darts. Suppose a drunkard keeps throwing darts until he hits the bullseye. The number of times he throws is a geometric random variable with P, this, all right. The waiting time. The geometric distribution plays an important role in the theory of queues or waiting lines. People study it very thoroughly for queuing theory. It has a lot of applications in computer science and also in business. For example, suppose a line of customers waits for service at a counter. It is often assumed that in each small time unit, either 0 or 1 new customers arrive at the counter. So this is an assumption. Basically, we do not assume arrival of batches, all right? So people just randomly arriving, they are not arriving in a group. So if I divide the time small enough, then basically either no customer or 1 customer at the most. So this is so I exclude the batch operations. So suppose then the time t until the next arrival has a geometric distribution. So it is natural to ask for the probability that no customer arrives in the next k time units. So no customer arrive in the first k units, meaning that your t has to be bigger than k, right? So this is the question here, all right? So probability of t bigger than k will be this. This is probability, okay, maybe I'll split it out. So probability of t bigger than k, right, means this. Instead of a summation sign, maybe I'll just write it in full, right? And so this is 1 minus p to the power k times p, and 1 minus p to the power k plus 1 times p. All right. And so in your slides, Q is equal to 1 minus P, so maybe it's better to do so. So I pick out the P, I pick Q to the power K, factor it out, so I will have this. So this is what we call a geometric series. Okay, and this geometric series will be summable if Q is between minus 1 and 1, but of course Q is always non-negative here. All right. This geometric series is summable. Okay, but this is okay because of this. And so the formula for this is 1 over 1 minus Q. So this is the common ratio in your geometric series. All right, and so 1 minus Q is equal to P, so this cancel with this. All right, so that is where your slides come in. Okay. Now, another way to calculate this without going through all these calculations, you can argue this has to be Q to the power K. Why? It says that the success comes later than K. What it means is then that from trial 1 to K, it has to be all failures and nothing else. Is that okay? And the two statements are the same statement, equivalent. I'm saying that the success occurs at time bigger than k. It's the same as saying that all my first k trials are all failures. So they are the same statement, but the second statement is easier to calculate. I'm saying that the first k trials all are failures. Then each trial is q, all k of them, q to the power k. That's it. So you don't even need to do these calculations. All right? So, yep. Acing and draw. So from an ordinary deck of 52 cards, we draw cards at random with replacement. All right, so the replacement is important here because if in a Bernoulli trials, we want the P to be fixed, to be constant, does not change from one trial to another trial. If I do not allow replacement, meaning that after you draw it, it will affect the probability of having an ace later on. Okay, so this is crucial in order to put ourselves into the framework of a Bernoulli trials. All right, and successively until an ace is drawn. So what is the probability that exactly 10 draws are needed, and what is the probability that at least 10 draws are needed? Now, what is the probability of success? This is actually waiting for success. So in waiting for success, the first and most important parameter that you need to know is the probability of success. In our situations, success is the same as getting an ace in a deck of 52 cards. And there are 4 aces, so 4 out of 52, then it is 1 over 13. So the probability of success is 1 over 13. All right? And in order for it to have exactly 10 trials, the 10th trial is reserved for success, which is 1 over 13. And then the previous 9 trials are all failures, so it is 12 over 13 to the power 9. Now this is just having a nicer way to write the numbers. A more intuitive way of writing it would be 12 over 13 to the power 9. You take care of the front part and then multiply the very last one, 1 over 13, which is your success. And here, to get the second probability, so this is this. Now, we have to take care of the fact that success might occur at 10. So a better way to reformulate this, either you use the formula or another way is x is bigger than 11. Okay, if x is bigger than 9, right? So what it means is if it's bigger than 9, which is the same as bigger than or equal to 10, right? And if it's bigger than 9, it means that the first 9 cards are all non-ace. That's it. So the first 9 cards must be 12 out of 13 to the power 9. Okay, so this is the R code. So this is the stem of the distribution. GEOM stands for geometric, and D stands for density, so for a point probability. And P stands for cumulative, but I wanted the right tail, so I have to subtract the left tail because I'll always calculate everything from the left, all right? Okay, bind 4D. Okay. I think Dr. Chu doesn't know that you actually twice a week. I think it's not twice a week, but it's 3 times a week. He probably doesn't buy 4D. All right. So a person buys particular 4D number. He only buy one such 4D number, but he buy it in a very regular manner, twice a week. All right. So every twice a week he goes there to buy it. So on the average, how long will the person have to wait to strike the first prize? Okay, I think you've seen the answer. So the answer is he has to wait something like 96 years. So one way to shorten his wait is probably to buy more, all right, to increase his chance of striking it. So if he just happy to wait for 10 years, then he should buy 10 times, all right? I mean, to increase the probability by 10 times, because the expected wait is 1/p. So if you increase the p by 10 times, you decrease the wait by 10 times. Okay, so if you haven't bought 4D, this is the numbers that you can buy from 4 zeros to 49. And so any of these numbers are equally likely to be drawn. Okay, and so you have this probability. So to get it right, because they are all together from 0 to 9999, you have 10,000 of them. So the probability of having it in the first prize is 1 in 10,000. So you have to play 10,000 times. All right. I don't know what is the price for the first prize. Is it 50 cents or $1? Huh? And what is the price? If the price is 10,000, then better not do it, because you have to play 10,000 times in order to get the $10,000, right? So you actually put down $10,000 in order to get back your $10,000. What if the wait is longer? This is the average, but the actual wait is actually fluctuate a lot, plus or minus your standard deviations. So plus or minus something like 10,000 times. Of course, you hope and pray that you might, but whether you should pray about it, I mean, it's another thing. You hope and pray that your wait is much shorter, because there is a lot of variations. All right, but you might be on the average you have to wait for 96 years. All right, so well. In the course of human history, I mean, this is short, but in your human history, it is very long. All right. Now, this is what we call a memoryless property of the geometric distribution. Let me explain the meaning of this. Okay. So here it says that you know that you have been waiting for at least, you have to wait for, I mean, your success hasn't come during the first n times. You've been waiting for it. So it hasn't happened yet. So for example, n is 10. And we are interested to see whether you have to wait an additional time of k. All right? All right? So the right-hand side says that it is the same as probability that your x is bigger than k. Now, to change it to something like we are more familiar, suppose you know that I have lived beyond n years. Then you wanted to see whether I would live another additional k years. Now, we know that we age, right? As a result, the probability is different from that I just live another k years. Suppose k is 10, and then n is, I mean, at least 50, all right? So I've been living more than 50 years, and you wanted to find out whether I will live another at least 10 years. Then, of course, the probability is not the same as just when I was born, and then I have 10 years, at least 10 years of lifetime, okay, because of aging. But here, the good things about certain things is in geometric, it is memoryless. I mean, as if the time that you have waited is forgotten. All right, you just don't have a memory about it. So it's as if this is the situations. Now, this is a lot of engineering modeling. Say, for example, light bulb. In a lot of first approximation of the light bulb behavior, knowing that your light bulb has worked for how many days, and then you want another additional days, it's as if the light bulb is just newly put there. All right, so that is the memoryless property. It did not remember that it has been there for 10 days. So now the calculation is very easy. Okay, we remember that this is q to the power n. And so as a result, this is unconditionalized the probability. And I change my n here to n plus k. And this is q to the power n. So this is q to the power k. And this is this. So the calculations, the proof is very simple. But I think it is best to keep the interpretation in mind, meaning that now for the light bulb, it is a good thing because it means every time when you turn the light bulb on, it's as if it was new, okay? But the bad thing is, if you have been waiting for your 4D strike first prize, you have been waiting for 20 years, it's as if you have not been waiting at all. So everything starts new. So if you know you have been waiting for 20 years, doesn't mean your strike would be 76 years. It means another 96 years, all right? So that is, it really depends on where you, what kind of situation you are in. Okay, I will mention about it and then we'll come back to this. So basically, our negative binomial random variable is just geometric, but I'm not interested in first success. In many cases, I want to accumulate many successes. So one of the things is you have your goal. Suppose, you want to work until you accumulate your first million. So this is a geometric, suppose, okay? It's very sad if it's geometric, meaning that if you have not reached your goal in 10 years, you start as new. So it's just, all right? But let's forget this. Suppose 1 million is not your goal, but you want 4 millions. Then what you can think of it is, each step is 1 million. So you wait for the first million, the second million, then the third million, and the fourth million. So this is your K. K is the user specified, all right? So in a negative binomial, you have two parameters, the probability of success for individual trials and the number of successes that you are waiting for. And once you have accumulated the K number of successes that you have specified earlier, you will stop, all right? So when K equal to 1, this is back to our geometric distributions, all right? So maybe I'll stop here, and then so we will derive it. Hopefully, by next week, we will finish the random variables thing, and something to look forward to would be more like a statistics thing, all right?